In this section, we're going to look at some applications of Taylor polynomials. So let's just remind ourselves of a few things. If a function has a power series representation at some center point A, then the coefficients of that power series have to be given by the nth derivative at A over n factorial. In other words, the power series representation is unique, and we computed that these had to be then the coefficients. This is called the Taylor series of the function at A. And just a reminder that the Taylor series represents the function on some interval. Now, it could be all real numbers. It could be some interval of the form x minus a less than r. So in other words, some interval centered at a, out r units on either side. Or it could just be the series is equal to the function at the center point and nowhere else. Those are three possibilities for convergence of this power series, and hence three possibilities for how this series could be equal to the function of f. So we just have to be careful when we start to plug values into the series that we know the values are equal to the function, and we're not plugging in values of x that are outside of the interval of convergence. Okay, so the next reminder has to do with using the polynomial now to approximate the function. So here we've got that the function is equal to the series for all x in some interval, but what if we truncated the series and only looked at, say, the first 10 terms or the first 20 terms? So we're looking at now a polynomial rather than a series. How good is that polynomial at approximating the function? Because ultimately our goal is to really say, if we have a function and it's kind of difficult to work with, hey, maybe we can replace it with a polynomial. What polynomial should we use? Well, we should probably use part of the power series representation. Okay, so we'll use a polynomial which is part of the power series representation, but how high do we need to take the degree? Well, it depends how accurate you want your approximation to be, and that will determine how high you want the degree of the polynomial to be, and that's what we're going to focus on right now. So just a reminder that we can always write our function f, if it has a power series representation, we could peel off, say, the first n terms of our representation. So now this is a polynomial of degree n, known as the Taylor polynomial of degree n. And that's not going to be equal to the function. There's going to be some remainder that we have as well. So the question really is, how good of an approximation is our polynomial to our actual function? Now, how big is this difference? How big are the function values compared to the polynomial values? Well, that's just the remainder. And so our focus is really on how big could the remainder be. If we have a small remainder, then that means the function value and the polynomial values are close to each other, which means the polynomial values are giving us a good approximation of the function. So we like small remainders. So the question is, how small is the remainder? Well, it will depend on the n that you take, how much of the polynomial or how much of the series you've used to form the polynomial, and then what's left over, in some senses where the remainder is coming from. And it also depends on x. And what Taylor's inequality tells us is how we can bound this remainder. It gives us an idea of how big this remainder is for n and x. And what it relies on is knowing the n plus first derivative. So once you've peeled off n terms of the series to form the polynomial, you've been using essentially the function and its derivatives up to the nth derivative. Then the remainder depends on the next derivative, the nth plus first derivative. If we can bound that on the interval we're interested in, then the remainder is bounded above by this quantity here. The bound on the derivative over n plus 1 factorial times x minus a. So how far x is away from the center point. Okay, the further you get away from the center point, you expect that your representation is going to be less accurate. This is a direct analogy from using the tangent line to approximate a function at a point. The further you are away from where you're constructing the tangent line, the less you expect the tangent line to be close to the function. You expect the function to pull away from it, but very close to the place where you've constructed the tangent line, or very close to the place where you've constructed the Taylor polynomial, you expect the polynomial to closely approximate the function. And the further you move away, you expect the approximation to be worse, so you expect the remainder to be bigger. Okay, so let's see how we can actually apply this. We'll see how we can use Taylor's polynomial and the remainder result to get some Taylor polynomial approximations to functions.